Good evening, everyone. Welcome to another session of the makeup class. We'll begin the lesson shortly. Let's just allow 2 to 3 minutes for the expected number of participants to be reached. Then we can start the session. Thank you. Good evening, everyone, once again. I hope you can hear me loud and clear. So, welcome to our second session for DCIT 207. For today's session, I've decided to break this into three parts, and if time permits, we will do all three. First part will be a briefing on the first slide. Then the second part will be an intro to the CPU OS simulator. And then we will learn how to add instructions to a CPU or a simulator. And I think that will be a good intro. And maybe if we all meet next time, we will learn to use it to run simple program instructions and then we proceed from there. So let's just delve into the history of computing. Mostly whenever this computing course starts, there is always a little history to be done. And since we've been doing this since first sem, level 100, it has become quite simple to remember the things that have been taught. So I hope you follow through to the end. It will just be talking. If you have any questions at any point, raise your hand and then they will be answered. My name is Prince Wilson. We proceed. All right, so computer architecture and computer organization. This course seeks to understand the in-depth operations of a computer, the parts where a user can see, the parts where a programmer can see, and then the parts that are hidden from second-hand programmers and users as well. The computer's organization is shown, what you see on the screen shows the different aspects of it. So there's a computer architecture, and then in there we have the architectural attributes, and they include computer organization, and we have organizational attributes as well. The computer architecture has sorry, good, attributes of a system visible to the programmer. So that's what the computer architecture is. They have a direct impact on the logical execution of a program. Then we have the architectural attributes, and they include the instruction sets. That's the number of bits they used to represent various data types, input-output mechanisms, techniques for addressing memory. Then we have the organizational attributes, which include the hardware details, transparent to the programmer, control signals, interfaces between the computer and peripheral memories, technologies used. And we have computer organization, that's the operational units and their interconnections, that's realized architectural specifications. So let's break these things down. We start with the computer architecture. It says attributes of a system visible to the programmer. So these are things that the programmer can see and then access. And then they are things that allow the program to directly communicate with the computer through logical instructions and then help them execute programs. Then the architectural attributes. These are instruction sets, your number of bits, the ones used to represent data in various forms, how you enter data, how you retrieve data from memory. So these two parts talk about how the user is able to interact with the computer, specifically the programmer is able to interact with the computer through a particular language using instructions. Then we have the hardware details, and then we also have the operational units, which have their own network of operations through which they function, and then they
Please, if you are speaking, we can't hear you. I think you are muted.
Please, good evening, everyone. Mr. Prince Wilson will be joining us shortly. So please, let's wait for him. Let's exercise patience. Thank you.
Hello, am I audible? Sorry, everyone. Good evening once again. Okay. My network was messing up. I'm sorry. I'm back. All right. Um, let's proceed from where we left off, shall we? Oh, shut up. Oh. All right. Please, if you can see my screen, drop a reaction so that we can proceed. Can you see my screen? Am I speaking? Am I muted? All right. Yeah, Mr. Joshua. Yes, please. You may let him in. Okay. You may let him in. All right. Let's
Okay, sir.
proceed. So let's look at some of the system architectures that have been built from times past till now. You are familiar with the IBM. Mr. Joshua Champo, Mr. Joshua Champo. Okay. So the IBM architecture was introduced in 1970. It included a different number of models. It could be upgraded to a more expensive, faster model without having to abandon original software. New models are introduced with improved technology, but they retain the very same base architecture that the originals were using so that the customer software investments are protected. And also, architecture has survived to this day as the architecture of IBM's mainframe products line. So what they're implying is that the very same formats of system architecture that they started out with for the IBM system has just been tweeted and then updated and upgraded. However, it has never changed its base form that the original stuck to. And then this system architecture has been used in or has been reproduced in every single other upgrade that they have done till this day. The structure and then foundation of systems. So then there is the hierarchical system, and then it's a set of interrelated subsystems. So there is a main system, and then there are smaller systems that work towards that main system, that is subsystem. The hierarchical nature of complex systems is essential to both their design and their description. The designer needs only deal with a particular level of the system at a time. So it's in a hierarchy. You address a particular region of the system at a time. And then it's concerned with structure and then function at each level. What is structure? The structure is the way in which the components relate to each other. So if you are dealing with a particular system and you take all the regions of it, how all the single components are outlaid and then have been designed to function is the structure. Now, the function is the operation of individual components as part of the structure. So you take different components such as the central processing unit, it has its function. And then you take a different components like the register or the RAM, it has its function. How these two things work together forms the structure of that architecture. All right. There are 4 basic functions that a computer can perform. The first one is data processing. Data may take a wide variety of forms and range of processing requirements is broad. What are some of the forms that computer data may take? If you know any, please raise your hands and share, okay? If you know any form of data that computers normally take as inputs or bring out as information. Forms of data, everybody. Forms of data, going once, going twice. Okay, at this height.
Can you say sound waves?
Sound. So sound. Sound is a form of data. That's correct. Please, who was that? Was that Mr. Abuaje?
Yes.
Yeah, thank you. Powerful. Yes, what else? Yes, Mr. Emmanuel, yes.
Yeah, can somebody say video?
Video is a form of data. Good. So video inputs data, sound, data. Is there any other you can share? All right. So then we have video inputs, we have text inputs, we have sound inputs, and etc., etc. So then all these ones are forms of data, and each single form of data must be processed differently. We understand that on the level of computer, low-level languages operate as on and off signals. This means for every single data you give to the computer, it has to convert it and then bring it down to a low-level language so that the computer can understand it as transistor signals on and off states. Therefore, each single form of data will pass through a different channel, but will eventually end up in the same form. This will mean that there are different system requirements to process different forms of data. So the data processing takes a wide variety of forms depending on, and because there are different forms of data that we give to computers. In today's times, computers are so advanced that you can speak to them with speech inputs, and then they take that, translate it to text, then they convert that text back into what do we call it, digital code, and then they understand it on their level. Then they are able to respond back, convert their response back into text, and sometimes even give it back out as audio input. So those of you who are familiar with AI tools, you know that the AI of today can take audio inputs. Somehow we know that computers are not supposed to even understand full words. However, somehow it's able to convert that into text, take that text to the machine language level, and then interpret it as something it can understand. It decodes it, gets exactly what you want, and then processes it, reverses the process, and gives you back information in sound. So then you see data processing takes a lot of toll on the computer, and it has a lot of system requirements. Then there is also storage. There is short-term storage and there is long-term storage. Short-term storage is done by cache, RAM, and then registers. And then long-term storage is done by device, what do we call it? Parts like the ROM of the computer. And we have data movement, inputs, outputs. When data is received from or delivered to a device, a peripheral. So peripherals are external devices that are connected to the computer. Okay, that is directly connected to the computer. Data communication. So we start with the input and output. When you are feeding the computer with something it should do, that is an input. When the computer gives you something else as a response to what you fed it, then it is an output. Data communication. When data are moved over long distances to or from a remote device, okay? And then we have control. A control unit manages a computer's resources and orchestrates the performance of its functional parts in response to its instructions. So you can view the control unit as like a bus conductor that is directing, or like the protocol people at church, telling this person where to go, sit here, sit there, sit here, sit there. That's a control unit. So it helps coordinate the movements of data and information among the CPU. And then, okay, we come back to the inputs and outputs. It says when data are received from or delivered to a device, a peripheral. What are some examples of these peripheral devices that we connect to the computer to be able to give it inputs and sometimes receive outputs? If you can name any, please raise hands and share a peripheral device that computers normally use.
Can you ask the
Oh, sorry. What is an example of a peripheral device that we normally connect to computers? Mr. Freeman.
All input devices like microphones, scanners.
Thank
What
you.
else? Digital camera, which you take a picture, you connect to input the pictures you take into the computer,
Excellent.
and recorders you connect to send your audio back into the computer to make your editing and all. All these
Excellent.
are input
Excellent.
devices. Yeah.
Excellent. Excellent. So then he has given some examples of the input peripherals there are. He mentioned quite a lot. He said webcams that you connect, microphones for audio input, keyboards, mice, etc., etc. What about audio peripheral, output peripheral devices? If you know any that we connect to the computer to be able to get information out of the computer. Either your hand was up, Mr. Felix Asante, or Mr. Asante. Sorry, your hand was up. You may answer.
Okay, so we have printer for output on a hard copy. We also have for audio we have speakers. For
Excellent.
graphics we have monitor or
Wow.
any
Excellent.
graphical user interface, that is
All right.
TV and all display.
All right. That's good. That's great. That's great. So all these are examples of devices that we use to communicate with the computer. So it means input devices are peripherals that we connect externally to be able to give information to the computer or data. And then output devices are what we also connect externally, output peripherals for the computer to be able to communicate with us, communicate instructions. Forgive me if I am talking too fast. Normally I speak fast. However, I slow it down for my lessons, but we are tight on time, and that is my fault as well. But listen fast, okay? I speak fast, so hear fast, adapt. And then if I am moving too fast for you and then you can keep up, just let me know. If it gets to the practical aspect, I'll move slow so that we can all take time. All right, so move. And then remember, the data communication is when you are moving the data over distances. Longer, even if shorter, it is still communication to or from a remote device. And then the control unit manages, as I mentioned, computer resources and orchestrates the performance of its functional parts in response to instructions. The director. All right. So now here's a top level structure of the computer. So we talked about the hierarchies. Yes,
please?
Mr. Yes.
Yes. Please, how is control unit a function of your computer?
All right. Thank you. So now we come back to the functions. The control unit is not the function. Control is the function. So for example, if you come back to the top here, you see data movement is a function of the computer. However, the devices that take care of the data movement. So if we go all the way back to the slides here, I want you to pay close attention. It mentions structure, it mentions function, but we also have hardware that take care of all these things. And then the hardware coming together, the components and how they relate, they form the structure. And then their functions are the individual operations. So now back to your question. If we take a function such as data movement, it is handled by devices like the peripherals. And then data communication is also handled by devices like the peripherals. However, we have control. It is also another function, but the control unit is not a function. It's a component that is responsible for that function. So the control unit is part of the organization, whereas the function it does is control. So control is one of the functions, but the control unit manages that function. Mr. AP, oh, please, what's the AP for? I've not seen the full name.
Prince
Appear.
Abuaji.
Oh, Prince Abuaji, okay, yeah. So Mr. Prince Abuaji, okay. So I believe the question has been understood. The
Yes.
answer has been understood. All right. Thank you very much for bringing that up. All right. We move. Top level structure of the computer. So now at the top, what happens at the top? What we will consider as the deepest level of the computer, that is the top of the computer's hierarchy. So now what happens there? Inside the system of the computer, we have three major functions or three major parts that play a role or on all of the computer. We have the input output parts, we have the main memory, and then we have the central processing units. Then we have the system bus. The job of the system bus is to move information between these three regions of the computer. So it takes from input, stores in memory, retrieves from memory, gives to central processing units. Central processing units processes data, passes it to memory to store there, all through the bus, by the way. Then, as it goes to memory, it is retrieved and given back to the input output so that the user can see it as a desired output. So remember, the bus is like a medium of transport, moving information between all these three regions. Is that clear? Then, breaking down the CPU, we have other regions. There is the internal bus of the central processing unit that connects three regions, as the registers, arithmetic logic units, and then the control units. From our previous lessons, we know that the registers are very fast memories. So their job is to be able to slow and speed up how a computer functions. The computer functions by storing data and retrieving it continuously so that the data that you give to it is not lost before the purpose of the data is met. So for that reason, it needs to do storage. And then if it's a storing, it means it has to retrieve. The retrieval must be as fast as possible so that the computer's functions will be optimal or it will not be too slow for the user. For this reason, we need faster memories and then closer ones to the central processing units so that it can easily access data and then retrieve them. That's where the registers come in. And there are levels of registers. We'll look at that later. Then putting the registers aside, so they are the memory. We give data to it. There is the arithmetic logic units whose job is for logic control, or in other words, logic processes. So then it does arithmetic processes and logic decision taking as well. So your additions, your subtractions, your multiplications, your and or all these operations are also handled by the arithmetic logic unit. Then we have the control unit. So remember, these three things are also connected by a bus, and this one is the internal bus. Then we come all the way to this side. We have inside the control unit, there is the sequencing logic, and then there is the control memory. So there is another storage medium here, that's the control memory. And then there is a sequencing logic that decides how the operation should flow. So then this one tells you that the control unit is indeed a conductor. That tells you move here, move that. And it does these movements by communicating with the buses at each level, telling the buses to transport this particular data to this side, to this guy, and to that guy. All right. We proceed. There are four main structural components of the computer. And then we are familiar with these ones. There is the central processing unit. It controls the operations of the computer and performs its data processing functions. If you remember what we said about the major functions of the central processing unit, we said it fetches, it decodes, it processes, it stores, we have all these functions that the central processing unit is supposed to be handling. So it says it controls the operation of the the computer and performs its data processing function. So it works like the brain of the computer. And then the main memory, you don't need to be told, it stores data. And we have the input output, and their job is to move data between the computer and its external environments. And there is a system interconnection, some mechanism that provides for communication among the central processing units, main memory, and input output. An example is the internal buses that we mentioned. All right. So the control unit, it controls the operation of the central processing unit and hence the computer. And there is the ALU that performs the computer data processing function. And there are registers that provide storage internal to the central processing unit. So then you should be very emphasis on this guy. Registers are also a storage medium, just like the RAM and the ROM. However, they are strictly working with the core and the other regions of the CPU so that they can speed up its function by retrieving data in the fastest ways possible. And then there is a central processing unit interconnection, some mechanism that provides for its communication among the control units, ALU, and registers, and that is the internal bus that we saw earlier. Then we have multi-core computer structure. In today's modern computers, you'll see something like Core i3, Core i5, Core i7. What are these things about? How are they so different from the traditional CPU systems that we are so used with? So it's the central processing units portion of the computer that fetches and executes instructions. It consists of the arithmetic logic unit, a control unit, and registers. It's referred to as a processor in a system with a single processing unit. The core is an individual processing unit on a processor chip. May be equivalent in functionality to a central processing unit on a single central processing unit system. It has specialized processing units, and they are also referred to as cores. So now, if you take a single CPU, its job is to run the computer. But sometimes we allot particular system CPUs for particular functions. In some computers, these smaller CPUs come together to form the major CPU. The number of smaller cores you have is what decides the core of your computer. So if you have 3 cores, i3 cores, so core i3, implying that, and then the core works just like the CPU. So it's technically, it's a CPU, a mini CPU. What this means is that your computer has the CPU, and then it has cores which are dedicated CPUs for running particular functions on its own. So you see, gaming computers, the ones that run high-end games, tend to have particular cores, higher grade ones, and it has different types of processors just for running high graphics games. Meaning to say that we have the central processing unit focusing on the computer's normal decisions, and we are allotting particular central processing units, which are the cores, to do particular functions that the normal core may find too tasking or may not be able to do. So they are specialized processing units, and they are referred to as cores. A processor is a physical piece of silicon containing one or more cores. It's the computer component that interprets and executes instructions. It's referred to as a multi-core processor if it contains multiple cores. In other words, if there are different cores coming together to make up that processor, it's a multi-core processor. Remember the word here, silicon. We are familiar with semi-metals in science, right? And we know silicon is a semi-metal. It has the ability to act as a metal or a non-metal in particular conditions. And for this reason, it has led to so many technological revolutions, like in solar energy generation. Silicon's ability to be able to transport currents under particular conditions makes it the perfect material to be used to trap light and then convert that to signals to move electrons to cause generation of electricity. It runs similar functions inside the computer, switching between a metal and a non-metal to help the computer's transistors function. So then, a processor is also made of silicon. Keep that in mind. A cache memory. Multiple layers of memory between the processor and the main memory. They are smaller and they are faster than the main memory. They are used to speed up the memory access by placing in the cache data from main memory that is likely to be used in the near future. So they are like a reference point, and then they shorten the distance that the CPU has to travel to retrieve memory. So for example, if I was doing 2 plus 2 times 3, And the computer starts by doing the 2 times 3 to get 6 before it adds the extra 2. The cache memory is going to first, if the computer does the 2 times 3, it stores that in a region that is close to the CPU and also stores the remaining data that we will need to combine, that is the 2, so that the computer does not have to travel all the way to the starting point to retrieve the data, but rather it will have to travel just a shorter distance, making its job faster. So then the cache memory is like a reference point, or like when you are playing a game, there is a save point, right? So that when you die, you can come and restart from exactly where you saved instead of going all the way back to the start of the game. So like a load point. The cache memory is like that very save point or that reference point in terms of the computer's management. So its job is to hold memory and data very close to the CPU, just like the registers. A greater performance improvement may be obtained by using multiple levels of cache, with level 1 closest to the core. So then there are different levels of cache. The smaller the number, the closer it is to the core. Level 1 cache are closest to the core of the computer. They are right there on the inside. And then the additional levels, level 2, level 3, they are progressively further. So then the higher the number of the level, the further it is outside of it. So level 1 is the closest to the core. Keep that in mind. All right. Here's a figure showing what a processor chip is like and then how it has several cores making it up. So then we have the motherboard, we have the memory chips, in other words, our RAM spaces, and then we have the input-output chips. Now, if we take the processor chip alone and we zoom in on it, you realize that there are the different cores making it up. So this one is a Core i8 because it has 1, 2, 3, 4, 5, 6, 7, 8. And then it has level 3 cache memories on it, so on the outside. And then it says if you take a single core and you zoom in on it, inside that single core, there is the instruction logic, arithmetic, and logic units, and load and store logic. What does this look like? It looks just like the CPU, right? So the core is basically a CPU on its own, and this one has 8. So now it says on that single core chip, we have the level 1 cache, the level 1 instruction cache, and then we have the level 1 data cache, and we have the level 2 instruction cache, and we have the level 2 data cache, implying that on the core itself, we have the closest cache there. This means, take a look at the distance here. If the core wanted to retrieve information during processing, if it's hard to go to the level 3 cache, it means the movement will be something like to this guy and back. However, we are already inside the core, we already have the level 1 cache. So if the data is not too large, it can be stored here immediately and then retrieved fast. If the data has a function, but the function is like in order of priority, it's a secondary to another, it can be pushed further to the level 2 or pushed further to level 3. And data that will need immediate retrievement in the near future, and the computer sees that this data will be really needed, it will be holding inside the level 1 data cache storage space. So you see the smaller the number, the closer it is to the core. So then we have the level 3 cache. It's on the processing chip. However, it is not directly on the core, but level 1 and level 2 are on the core. This tells you that they are very close to the core itself. And then remember, their job is to speed up the function of the CPU by setting a save point where it can easily retrieve data. A motherboard with 2 Intel quad. So then, here are your cores. These ones, not the fan, oh my people, not the fan. This is a, what do we call it? A whole board showing different regions of the computer. If we trace it carefully, it says 2x quad-core Intel Xeon processors with integrated memory controllers. And then they are studied behind here. It says 6-channel DDR3 memory interfaces up to 48 gig on this side. And then it shows several other data. But then your main focus should be the core. The core is not the fan. Okay, I believe it is somewhere behind it. So it is not the fan itself, it is somewhere behind it. Okay. So do not take the fan as your core, please. The fan is a cooling system. So the job of these fans is to reduce the heat inside the computer. All right. Here is an outline that we can use to observe the arrangements of these things properly. So then we have our cores here, started all over, right here. And then we have different levels of cache also present on this one here. So this one shows you how taking a single processor unit chip, how many cores can be fitted on it. This means to say that a single processor unit, if it has higher cores, then it has higher processing power. So someone with a device that is a Core i7 should, in the normal sense, have a higher processing power than someone using a device that is i3. So the functions that an i7 can run fast, it will be a bit slower in an i3. And sometimes, not even a bit, it can be exponentially different. And those of you who are into gaming that have particular types of dedicated RAM storage and then dedicated cores for running games smoothly, you will testify to the fact that running a game on a gaming computer is totally different from running a game on an average PC. Do I have any gamers on the in the meeting right now? Okay. The person I'm looking for is not here. Okay, Mr. Joel. I see, yes. That's right. Support man, it's true. This guy is a baller. Yeah, it's true. Let's proceed. And then, okay, here's the IBM, also its layout too. Okay, we'll look at all these terms later. I'm sure some of them you're already familiar with. But then, this is what it is. We proceed. Let's move fast. History of computers. We are not going to go deep into this. The first generation of computers used vacuum tubes. IAS was one of the earliest well-designed computers. It had a fundamental design approach and it was using the stored program concept. It was attributed to the mathematician John von Neumann, and then the first publication of the idea was in 1945 for the EDVAC. The design began at Princeton Institute for, so go and read this one on your own, okay? These are basic stuff. Completed in 1952, the prototype of all subsequent general purpose computers. So it sets the foundations for most of the computers of today. The von Neumann architecture was very advanced, even for its time. And then that build led to or inspired the development of a lot of the type of computers we are using today. All right, we proceed. General structure of the IAS computer. So let's look at it closely. So the central processing unit right here. Inside of it, we have the arithmetic logic unit, and then it has the accumulator, and then it has the multiplication quotient. So if you hear terms like multiplication quotient, you know we are doing addition, subtraction, right? So that's also a register. Arithmetic logic unit is doing operations. It runs them through this side so that it will be able to process those things, feeds them to the accumulator. The accumulator is a place, where data is stored and also worked on during calculations. Okay, and we have the memory buffer register. We'll look at all these things later, but the memory buffer register is like the memory data register. They're basically the same thing. It holds data as processing is being done. And then we use input and output equipment to feed and retrieve data from the computer. If you come to this side, there are several different memories that we are endlessly feeding data to and retrieving. So when it comes to the memory buffer register, feeds to arithmetic logic units, goes through the multiplying and then quotient register, feeds to the accumulating register, feeds back to the arithmetic logic unit, feeds back to the memory buffer register. It's a chain, endless chain. And once the result is achieved, it is fed to the output device and the user sees it, right? And then we come on even further inside the program control unit. So then you see the control tells the data how to flow. And we are already familiar with some of these terms. Program counter, instruction buffer register, instruction register, memory address register. All these things here, their job is to just maintain flow and prevent the computer to running into an overload and then crashing. So then the program counter, we know its job is to hold the address of the next program. Memory address register holds the address of the current memory that we are dealing with. The instruction buffer register holds the what do we call it, exact instruction, and then the instruction register holds the instruction to be executed, and then the control unit coordinates the movements of all these things using the correct signals. So then there are keys here that you can use to know the meaning of all these things. Go and look into that later. AC is the accumulator register, MQ, multiply quotient register, MBR, memory buffer register, also known as memory data register, IBR, instruction buffer register, program counter for PC, memory address register, and then instruction register. I'm sorry if I'm moving too fast, but there's no time, okay? I want to show you a little something even, if not, okay? And then we have learned about data. In data, what do we call it? Digital, how to operate on data. We learned about sign data, etc., etc. If it's needed later, we will review these things again, okay? and blah blah blah, so many things talking about how these registers work, and then blah blah blah. Go chart to show how the data moves between them. This is important, so let's look at it. If you are given an instruction, the instruction starts from a starting point, and then it is according to, so there's the start points right here, and then it says its next instruction in the instruction buffer register. If the instruction that is supposed to be executed has been fed to the instruction buffer register, we will go down this lane. However, if it has not, we will go to the program counter tells the computer that memory address register, go to the next address. And when it reads the next address, the memory address register also tells the memory buffer register, which has the data, to bring the data to this particular address so that we can have it. And once we have the data, we are able to channel the data through the right places. And then finally, we will process it using the right instruction from the instruction register, and then we will feed it back to the user. There are several processes it runs through. We know computer has data first. The user gives the computer some data. Once the data enters the computer takes that data. The program counter initially holds the 0, implying that we are now starting at step 0. But immediately the first line of program is run, it moves on to point 2. So those of you who joined my first lesson, when we're using the little man computer, we could trace the functions of the program counter. And it's a little different from how the instruction register works, because we know that the instruction register, unlike the program counter, it doesn't hold exact spaces. It doesn't tell you that we are going to instruction on line this or line that, but instead it holds the opcode of the instruction to be executed. And then the accumulator does the calculations and stores the data in the process. Memory address register holds the address of the data to be executed. And the memory buffer register holds the exact data that we are going to execute. So I missed the last lesson, but I had some people asking questions concerning what the memory buffer register will be in the little man computer. So in the little man computer, the little man computer's equivalent of the MBR is the MDR. So the memory data register is the memory buffer register. It's the words can be used interchangeably, and then don't worry, they are the same thing. So if you have studied, you see when MBR is used, MDR is not used anywhere. So they are basically the same thing. All right. These are some opcodes for particular instructions. And then some of these codes will be held in the little man computer. A smaller part of the codes were held when we were doing what we call it, simple functions like additions and subtractions and etc. etc. But these are 8-digit codes. So then 8-digit codes representing every single one of the data here. So we see whenever we enter these things, and then from Mr. Freeman's lesson yesterday, he mentioned that some of these things have been encapsulated, hidden from the user, so that they do not need to see exactly what is happening in the background. If I am stating this right, Mr. Freeman, am I stating this right?
Yes, please. All right.
Yes, boss. Yes, boss. So it says when you say something like load to the computer, you have no idea what the computer interprets that data as. But then to the computer, you have given it a code. In other words, electrical signals, because 0101 are actually going to be converted directly into transistor states, on and off, on and off. And then it interprets that as, okay, transfer the contents of the register that has been labeled to the accumulator to be added. So these things are happening behind you or in the background, and then the computer just gives you the straight up face response, and then you just see it happening. But then these data have been covered somewhere, you just do not see it. All right. All these things, some of them we are familiar with. We know load retrieves data, stores data. Jump will move from one data point to another without even obeying what do we call it? The program counter tells it. And then adds and subtracts and etc. etc. All right, let's move on. Logic, storage. Thank you. Whoever that was. All right. Logic and then storage also. So the fundamental computer elements, there is the Boolean, logic functions. We know these ones to be the true or false states that operates. Is this Mr. Please, who is that? Please mute your mic. Mr. Joshua Champon. Mr. Joshua Champon. Hey, Charlie, Mr. Joshua. This one is becoming a little too much.
Charlie, I'm not the one. No. I'm not the one. Please check the name. Oh.
Are you sure? Okay, sorry. I can see two JAs here. So, all right. Mr. Dijabo, I'm sorry. I'm sorry. I'm sorry for misidentifying. All right. I'm sorry. Whoever it is, you are making me blame somebody else. I beg, mute your mic, okay? Mr. Joshua, my apologies. All right. The Boolean logic. Hey, Chewan. The Boolean logic is what tells the computer how to operate. At least it tells the computer what the user is trying to say the computer should do. So it uses functions like AND, or, not and, not or, exclusive or, etc., etc., to tell the computer how to flow and activate its signals. So on and off states, turn on two O's, turn on one O, turn on blah, blah, blah. These things are decided by the Boolean logic. And then we have the binary storage, which reads and writes data and holds the data as it is being processed. And then finally, it is given out as an output. So these are the fundamental computer elements. And then we have ICs, integrated circuits. We learned in the generation of computers that along the way came these guys. They store data, etc., 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 etc. There's so many things. I'm going to pause on the slides over here for today. Then I'll take you and then introduce you to the computer CPU operating system simulator. I know most of you are here for that exactly because it is quite a complicated setup. And then I do not know how the last lesson went. I don't know whether the lecturer taught you how it should run, or if he taught you how to add codes or add instructions, or etc., etc. However, I'll use the little time I have to it's 9:07, that's far past time, but let me just take about 8 minutes to 9:15 to show you a few things concerning that. I'll introduce you to the concepts. I'll share a file later on the platform for the paid participants, and then those who can access that file, use that file, and then try to understand the individual regions of the interface you see when you open the Central Processing Unit OS simulator. There is something about that system. It is far different from the Little Man computer. The Little Man computer is also a simulator that shows you how the Central Processing Unit works. However, it does it on a small scale that is very humanly understandable. The central processing unit operating system simulator shows you the central processing unit's functions as well as how they relate to the operating system. And it shows you in more detail. So despite the fact that it is also a simulator, just like the Little Man computer, its detail is far more than what you see in the other. Therefore, it might appear as a very complicated setup. And then you are reasonable to, it makes sense if you say this is quite complicated, because it is, yes. First, I'm going to show you a file, and then we are going to use that file to understand just exactly how these regions of the thing works. And once we understand that, next time we meet, because our time is already up, we'll look at how to load some instructions, and then if time permits, perform some simple operations using that. Do not worry, no matter how confusing it gets along the line, our class will always be here for you, and you can come and join us, and then I will explain everything to the best of my ability. And then even if my explanations are not fit for you, I will look for some videos for you, and then I'll come and provide them some Indian tutors. They will tell you what to do. They are very good. Even if you don't want them to tell you what to do, they will tell you. All right, so let's proceed. So this is a small slide, and then there are different parts of it. It's a model that shows you exactly how the CPU simulator works. So it's like a tutorial model. So let's get right into it. So it talks a few things about what we have just talked about. Is it the computer architecture tutorials are supported by simulators, which are created to help underpin theoretical concepts normally covered during the lectures, blah, 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 blah. So for now, let's just discuss theory, okay? The details of the simulator, there is the CPU instructions memory. Take note of that. Special CPU registers like the program counters, and then the instruction register, etc., etc. And then the CPU general purpose registers, you'll see them later. So if you have opened the interface, you see the general purpose registers. They are the ones labeled as R00, R01, R02, R03, etc., etc. And then there are the program stacks. And then this will take us back to Professor Solomon's second semester with us. Was it Professor Solomon? Talking about how data is stored, and talking about trees and family system, etc., etc. And he mentioned how we can store data in stack form. And then we have the push stack, and then whatever, and then load from bottom and load from the top. If you recall all those things, some of those concepts are applied in this actually. All right, so then this is the first page, or this is the front page that you will be faced with if you open your this thing. Am I correct? This is it, right? This is exactly it. This is what you see. Now let's look at the individual regions. Starting from this side, this region here is called the CPU instruction memory view. Take note of it. And then we have other regions here, the special CPU register view. So we have the program counter, we have the base register, we have etc., different ones. And then we have the CPU registers view here, on this side, sorry. So then you see the registers labeled as R00, register 1, registers 2, etc., etc. There can be a different number of registers. Some computers have only 8, or some CPUs, sorry, older systems. And then more recent ones can have up to 128 and beyond, etc., etc. And then we also have the program list. So whenever you enter a program, you're going to see a list will start to be formed here. We'll see that one too later. We can add instructions on this side. We'll see that later. We can create programs on this side. It says the parts of a simulator relevant to this are described below. Let's read this carefully before we are able to identify the parts properly. There's an exercise that follows, but the exercise is something you may not be able to do. However, I believe some of you can do it, given them the right amount of time. So let's start with the CPU instructions memory view and see what exactly it's about. This view contains the program instructions. So we do not type programs here. So unlike the little man computer, you are unable to directly type into these columns. You are going to have to add your code strictly at strict places. So it is very close to an actual CPU. That's what they are trying to make you see. It says the instructions are displayed as sequences of low-level instructions, mnemonics. You know the mnemonics like add, ADD, halt, SUB, etc., MOV for move, etc., etc., and not as binary code. This is done for clarity, and it makes the code more readable by humans. Each instruction is associated with two addresses: the physical address, which is written as PAdd, and then the logical address, which is LAdd. This view also displays the base address against each instruction. The sequence of the instructions belonging to the same program will have the same base address. Now, we are aware of the program counter, and then we know how it controls flow and how it can point out to particular regions inside the, what we call it, even storage. And then the base address is over here. The base address also holds the particular region where it wants the computer to start execution from. So it sounds like the program counter. Program counter holds the next address so that the computer knows where to go. But then the base address inside this one, it combines the values from the base address with the values from the program counter in order for it to give out the physical address that the computer is going to use. So inside the little man computer, the physical address was a simple concept, and the program counter was also a separate concept that was just directing flow. But on the inside of the computer, we combine the base address, which can be it can be at any starting point. So in the little man computer, we're always starting from 00. But the base address in this case can start from even 100. It can start from anywhere. In order to know the exact physical address where the computer will start, you will need to combine the program counter value plus the base address. And that is what tells you the exact address or the exact physical address that we're going to start at. This will make more sense when we start working practically. So the sequence of instructions belonging to the same program will have the same base address. The special central processing unit registers view. This view shows the set of central processing unit registers, which have predefined specialist functions. There is a program counter, and then it contains the address of the next instruction to be executed. We know this already. Instruction contains the instruction currently being executed, and there is the status register. It contains information pertaining to the result of the last executed instruction. So what we did last, what is it about? Did this work through? Was there an error, etc., etc.? And there is the what do we call it? A status register. We just talked about stack pointer. It registers points to the value maintained at the top of the program stack. So if you remember what I mentioned about what Professor Solomon was teaching us back in the day, the stack, he mentioned that data can be stored in stack form. In other words, they are piled on top of each other. And then sometimes we can retrieve them from bottom or retrieve them from top by popping. If you remember that, the terms he used, pop. Okay. We'll come to that later. And then there is also the base register. It contains the current base address. The memory address register contains the memory address that is currently being accessed. So it's different from the base register. Base register holds an address, combines that with the program counter to find exactly where the computer will start execution. Whereas the memory address register holds the address of the current points in the memory that data will be addressed from. There are two different regions. One can tell the computer where it should start execution, whereas one tells the computer where the data is stored. So the memory address register tells the computer where we are using, and then the base register will tell us where to start in coordination with the program counter. And then we have the state source bits, the overflow, the 0, and then the negative bits. We'll come to this later, but then they have to do with actual values. When you add, if you remember overflow, when you do addition of two numbers in 8 bits or 5 bits, and then it ends up breaking into 6 bits, then we say there is an overflow. A carry, sorry, that's a carry bit, but technically it's an overflow. And then zeros and negative and etc. We'll look at that too later. And then we have the registers view. The registers here are the memory points that we're talking about. That makes it very simple for the CPU to run its operation quickly. So the register set view shows the contents of all the general purpose registers, which are used to maintain temporary values as the program's instructions are executed. The registers are very fast memories that hold temporary values while the central processing units execute instructions. So then remember that they are like save points, just like the cache. This architecture supports from 8 to 64 registers, and these registers are often used to hold values of a program's variables as defined in high-level languages. Not all architectures have this many registers. Some have more, example 128, and others have 8. This view displays each register's name, a register, its current value, val, and some additional values which are reserved for program debugging. And we will need this for when we are adding instructions later. Take note of that. And then we have the program stack view. The program stack is another area which contains temporary values as instructions are executed. And this is one of the very terms that Solomon mentioned. He says the stack is a LIFO, last in, first out data structure. So it is also used for efficient interrupt handling and subroutine calls. Each program has its own individual stack. So you can view it as this guy right here, all of this region here. If we start stacking data into it and it enters as 1 here, the first data will drop all the way to the bottom. And the one that follows will come here. The one that follows goes above it. The one that follows goes above it all the way to the top. This means if we want to retrieve data in order, we are going to have to start from the top. And remember, the top is holding the last data you put in because the first data has sunk to the bottom. That's why it says the last in, the first out data structure. So this is one of the forms of stack registers there are. All right, the CPU instructions push and pop are used to store values on top of the stack and then pop from the top. So storing is adding and popping is taking away. These are simple terms, but they mean a lot. And also, when we are working, we learn to remove program. That one we'll do it practically later. This region here is where we start adding instructions. The program is where we start adding a new program. You add a program name, etc., etc. If you click on instructions, you'll be allowed to add an instruction. So today I'm doing this. Next time we'll jump right into the lab, and then we'll do a lab so that we can be ahead of the lessons before we meet. I'm going to end the lesson here for today. And I know I have been rushing. I've been tight on time because I was doing other things. Not like they are more important than this lesson, because after all, you're paying for it. I'm sorry for the network break that happened when the lesson was beginning. I'm sorry if I went too fast than you could understand. The recorded video uploads will be done today. We are sorry if they were not uploaded earlier. I thank you for your time tonight. If you have any questions, please feel free to ask now or remain silent forever.
Hi. Can you uh,
Mr. Abayo Prince, please, your network is breaking up. Can you come again?
can you hear me?
Yes, please, I can hear you.
Yes, I was saying, could you scroll up? I want to look at the exercise there.
The exercise, okay, that's cool. So I'll be sharing this, okay? So this is it. It gives you detailed exercises that you can follow to train yourself slowly. And then it also shows, I'm coming, please let me scroll further down so that you see something. Thank you for mentioning this. Am I audible? Am I muted? Am I speaking clearly?
Yeah, we can hear you.
All right, thank you. It goes further to show you an appendix where it stores, tells you exactly what each instruction can do inside the data sets. Okay, inside the what we call it CPUOS simulator. Okay, so this one and the CPUOS simulator has a very complex interface as compared to the little man computer. So when you're working with it, try to understand these things before you do your this one. Else you will get discouraged. So you will think this is beyond me, but it's not actually. With practice, you can do it. Okay, so boss, these are the exercises right here. Okay, can take a look at them.
All right.
All right, please. Is there any other question? All right, so with no further questions, I would like to end my meeting here. I hope my um my mediocre lesson has at least been able to throw some lights on concepts that you were unable to comprehend. Or even if you did understand, you have understood better. Auntie Vida, good evening. Please speak.
Good evening, Mr. Prince. Please, can you share this thing with us, the simulator,
The
the
simulator.
yes,
Okay, so I'll be sharing.
the
So,
one, yeah,
sorry, please come, proceed.
please,
Oh, you
the
may speak.
one you just,
All
the
right, the
CPU
files.
simulator, yeah.
All right, so I'm going to show you I'll share the file and I'll share the APK to the simulator so that you can install it on your system in about 5 minutes,
No,
okay?
I have already installed it. I need
All right, the file.
the file. Yes, please.
All right, so I'll pass the file to you, okay? I'll pass the file to you.
All right, sure. Thank you
All
so
right,
much.
anybody else? All right, no problem, no problem. Anybody else wants to speak? Mr. Freeman, Madam Oponwa, Madam Monica Mama, Mr. Emmanuel, Mr. Joshua Champong, Mr. Prince Carl, Mr. Joe Akota, Mr. Joshua Fia. Is there anyone who would like to speak? All right, so have a great night, people. I'll be sharing the files. Try to practice in your own time. See you next time. God bless you all. Goodbye.
Bye bye. Thank you so much.